All right. Good. Yeah, let's break the silence. Hi, everybody. My name is Jerónimo Castrillón. I'm with TU Dresden, and it was an honor for me to be the program chair of this year's LCTES. So welcome, everybody here. I think we have a great program. Let me give you a quick set of slides about a bit of history, about a bit of thanking a lot of the people that contributed to this conference, and we get a peek into the program. So yeah, it's the 27th edition of LCTES. It started actually as LCTRTS. It had sort of languages and compilers and then real-time assistance in the title in the past. Since 2002, it is a conference, and there was a word added theory to the name in 2012. So if you see, this is a list of very interesting locations where LCTES was held, and today we are here in Boulder, Colorado, my first time here. It looks like a very scenic place, and so very happy to be here. All right, so I was the program chair of this conference, but there's a lot of work that happened behind the scenes, also by the general chair, J.J. Chen, who is here as well, the program co-chair, Christian Dietrich, who couldn't make it, publicity chair, Seong-Kyung Heo, and today, and this year we had also an artifact evaluation part, which was headed by Petra and Benedict. Some of you, the authors here, interacted with them for the artifacts. So big thanks to this sort of organizing team. Also big thanks to the steering committee of LCTES, headed also by J.J. Chen, who is here as well, as I mentioned. So you see it's about a pretty diverse group of individuals, many of whom I guess you all know. Good, of course, it's really important to have good reviews, and I think this year the discussions on the papers, the reviews were pretty on time. So big thanks go to all the members of the TPC, of the Technical Program Committee for this conference. So I hope you as authors, the ones that are here in the room, I hope that you got valid and valuable insight from the reviews. From my point of view as program chairs, I think the reviews were pretty fair, and also the discussions were very fair, and yeah, I hope that you guys had a good experience with reviews. So second page of reviewers, a bunch of reviewers, as you can see. Now to the submissions. So we got, in the end, 42 full paper submissions. Those are the 10 pages papers, and we got 12 work in progress paper submissions. Those are smaller papers, 4 pages. In total, we got like 196 reviews collected. That means that every paper received like 3.6 reviews on average, a little bit lower for the WIP. So actually, the full papers, most of them received 4 reviews. Every TPC member reviewed from 5 to 7 papers, and all of this happened within a month. So I think that's, we were very proud that we actually managed to meet all the deadlines. In terms of acceptance rate, full 15 papers were accepted, so congratulations to all of you that got your papers through. And on the website, 4 papers were accepted. So in terms of acceptance ratio for the full papers, pretty similar across the years. So we got 1 paper less than last year with the same amount of full paper submissions. So it got a bit tougher this year. So but with 15 out of 42 is actually a pretty acceptable acceptance rate. You see that 36%, which is more or less what LCTES has been moving in the range in previous years. All right, as I mentioned before, we had artifact evaluation this time as well. So it was reintroduced last year in Seoul. There was this A committee headed by Petra and Benedict that I mentioned before. At the end, we had 8 submissions, so 8 papers, 8 full papers submitted artifacts. They were evaluated by a committee composed of 10 senior PhD students, postdocs, and some professors as well. It was anonymized, all the communication with the authors, and there was also online discussions to see which badges to grant these papers. And in the end, 5 papers of the 8 that were submitted got all the 3 badges, and then you have some other papers with 2 and 1 paper with with only one badge. So I think this is great. It's amazing. Thanks to the authors to put the effort in sending artifacts. I think artifacts are really important in our area of compilers, tools, and stuff, so they can reproduce results. Good. Okay, let's take a quick check into the program. We're starting today with these opening remarks. We're going to move directly into the first session of the conference, which is going to be about compiler tuning. After break, we're going to move on with the second session on binary optimization system security. Here we have 3 short paper presentations. And unfortunately, the first short paper presentation is going to be online, because at the end there were some issues with visas. Tomorrow we start with the keynote, which is going to be given by Aviral Chibrastrava. We move on with the session 3 on formal methods and system reliability. And we have 2 more sessions, one on specialized hardware and accelerator design, and one on memory efficient and control flow analysis. So I think we put some effort in sort of adjusting the program, as we usually do as program chairs. And I think the program, all in all, is quite interesting. So I hope everybody will enjoy this. On the keynote, as I said, it's going to be given by Aviral. That's tomorrow at 9, so don't miss it. It's going to be on practical quantum machine learning, overcoming the bottlenecks of scalability and stability. So I think it's a pretty interesting topic. So see you here. And then maybe to close up these opening remarks, big congratulations to these 2 papers. These are the 2 papers that were nominated for the Best Paper Award of the conference. So this was based on, first of all, of course, the overall review marks that we got from the TPC. Also, the TPC members could suggest papers as potential for Distinguished Paper Award. In the end, we narrowed this to more or less 6 papers, 8 papers. We created a committee to check the different reviews, to check the papers again, and we narrowed that down to 2 papers, and the winner will be then announced in the closing session once we have seen also the presentations for these papers. But I think if the authors are here, not sure, but maybe already a quick clap for the nominations. And also on the awards side, I mentioned that we were very happy with how the review process worked. Of course, there were also things that were not as good, but these 2 reviewers were particularly engaged also in the discussion rounds and so on. So in LCTES 2026, Klaus Schneider and Jung-Wook Choi will be awarded the Distinguished Reviewer Award. And this also, like the award, giving up the awards will be in the closing session tomorrow. All right, so that's all I wanted to share with you on the sort of the history and the organization of the conference. I will just hand over to the session chair, Meng Kyung, who will share this first session. So yeah, maybe get this.
Now let's move on to the next second talk. The speaker is Rizi Huang, and the title is a causal tuner feature aware. Mic. The title is a causal tuner feature aware causal guidance for compiler auto tuning. So please begin when you are ready. Okay.
Okay. Good afternoon, everyone. This is Richard from the Peking University, and this is my pleasure to present this work on behalf of Jiaqing Zhong from the National University of Defense Technologies. Because due to the visa issue, she cannot come here, and I will, on behalf of her, for the presentation. And the title of the work is a causal tuner, future-aware causal guidance for the compiler auto-tuning. Yes, we all know the compilers are the bridge between the human intent and the hardware execution. So it acts as the fundamental arbiters of the performance, portability, and the productivity. By applying optimizations like the instruction reordering, loop unrolling, and the constant folding, we can fully exploit the modern CPU pipelines, the cache, and the parallel capabilities to speed up the program. However, the modern compilers like LLVM offers hundreds of optimization paths. Relying on the standard optimization levels like O3 often fails to deliver peak and application-specific performance. Because these standard optimization are designed for a general purpose instead of for the specific workload. Therefore, this brings us the phrase ordering problem. We need to select the right paths as well as the right order to achieve the optimal performance. Considering this example, if we apply the constant propagation before the dead code elimination, we could create a clean and optimize result. But conversely, if we revise this order, we may fail to remove the intermediate code. However, solving this problem is notoriously difficult. Currently, there are two main approaches, the machine learning-based and the search-based. The machine learning-based approach uses predictive models to guide the search or directly generate the optimal configurations. And the search-based program will search the configuration space to generate optimal path sequences. While the machine learning-based approach struggles to generalize across different programs, the search-based can easily adapt to any target program. So in this research, we focus on the search-based program. Though the search-based method could easily adapt to any program, but they still suffer from three key problems: the combinational explosion, the spurious correlations, and the search blindness. First, the combinational explosion means that the LLVM path permutations are very, very large. With over 100 LLVM paths and the sequences, there can be many paths long. The number of the possibilities grows like p to the L times L factorial. That is exponential as a factorial growth combined. To make the things worse, the evaluating just one candidate could mean completely binary wrong, which is painfully slow. So with a limited resource budget, an exhaustive search is completely unacceptable. Second, The superior correlations means that in the iterative search, some approaches use the models like the random forest or the Bayesian methods to narrow down the search space. However, they only identify the paths that are correlated with the performance without understanding the underlying mechanics. This often leads to the model to mistake the statistic noise for a genuine and causal improvement. So we can find that the correlation is not equal to the causation, and just relying on the correlation will be misleading. Therefore, we must address this to ensure a more robust and explainable tuning result. And finally, the traditional algorithm suffers from the search blindness because they treat the compiler as a completely black box. First, they cannot reuse the historical knowledge, forcing them to rebuild all configurations from the scratch for every new coming programs. And they are unaware to the code features, wasting the identical search budgets regardless of whether a program is loop bounded or control flow heavy. This brute force exploration incurs prohibitive overhead while completely missing out the structural clues that could prune the search space. Therefore, to address these limitations, we propose a causal tuner framework as illustrated in this figure. It executes across three unique stages: the clustering, the synergy clustering, the causal mining, and the rule-injected online search to achieve a future-aware compiler auto-tuning with high sample efficiency. The stage one in this framework is the synergy clustering, which aims to alleviate the combinational explosion by clustering the programs based on the local pairwise path dependencies. And the stage two is the causal mining. It utilizes the fast causal inference to screen out the superior correlations and discover the robust causal rule size. And the stage three is a two-phrase rule-injected online search. It reduces the search blindness by leveraging the active causal mappings to guide the online search and eliminate the unpromising optimization branches. So let's look details to the framework. The stage one reduces the search space through key steps. First, the synergy matrix construction profiles the path sequences pairs to capture the order-sensitive interactions. It identifies the combinational benefits whenever TA plus TB is larger than TA and B. And then the subsequent extraction uses a greedy path search on the aggregated cluster matrix to extract and keep the top K unique maximal sequences. And finally, the cluster predictor utilizes a GNN-based embedding as well as a hierarchical clustering to group the similar programs for the targeted optimizations. The stage two focuses on the mining causal rules. We utilize the fast causal inference to recover the structural relationship by testing the conditional independencies. It is highly robust against the hidden confounders. Looking at the workflow in the left figure, the input data goes through the independence tests to generate a directed PAG. This process leads directly to the causal purification example shown in the right. The FCAI could effectively identify and cut off the spurious correlations introduced by the program feature F, as well as the corresponding statistic noise. And by eliminating these misleading passes, we could successfully capture the true intervention gains data, allowing us to discover a robust causal rules for the future compiler tuning. And the stage three introduced the two-phase rule-injected online search. It contains two phases. The phase one is causal subspace sampling. It bypassed the traditional co-star problem by prioritizing the search within low-dimensional causal manifolds. It maps the static features directly to the causal size and extracts the highly optimized state pipelines within the first 50 iterations. And the phase 2 is the residual evolutionary fine-tuning. It employs the stratified mutation rates to protect the verified causal gains while aggressively exploring the residual space. Specifically, we found that the conservative mutation rate of 1% to 5% will lock in the core causal structure, but an aggressive mutation rate of 15% will shuffle the unverified options to escape the local optima. We evaluated our framework on an AMD platform using the LLVM clone with the standard O3 optimization as our baselines. For the future data collection, we extract the program characteristics directly from the unoptimized LLVM bit code that are compiled at O0. By leveraging the LLVM's inst count and print loops passes, you could generate the standardized statistics via the states JSON option. And our evaluation crossed a comprehensive benchmark suites, including the C-bench, Pauling bench, spec CPU, and we also include the Llama bench from the Llama C++ ecosystem to ensure a thorough validation across diverse workloads. And our evaluation focuses on 4 research questions. First, we want to know how does the causal tuner compare with other auto-tuning approaches in terms of the overall performance. And second, we would like to know how do individual components of the causal tuner contribute to its overall performance. And the third, regarding the generalization, we want to know can the learned causal rules generalize to the unseen workloads beyond the training site. And finally, for the interpretability, we want to know why is the causal guidance mechanism in the causal tuner effective? And in other words, can we interpret what the causal tuner learns? Addressing the first question, we analyze the overall performance and the convergence velocity. Across the 30 diverse workloads spanning the classic benchmarks and the modern LLM engines, the causal tuner delivers a dominant 17.77% average performance leap. It comfortably surpassed other approaches such as group tuner from the last year LCTES, as well as other methods such as Bayesian-driven BOCA. Crucially, by turning the exploration via the offline injected causal rules, the causal tuner achieves a 14.30% speed up within the first 50 iterations. This shows that the causal tuner could successfully conquer the notorious cold start problem of stochastic searches. And we also isolate the individual components of the core components in the causal tuner. The ablation study reveals that the synergy clustering in the stage 1 and the causal mining in the stage 2 fulfill the orthogonal yet deeply complementary roles. Eliminating the synergy clustering will restrict the long-term scalability. It will cause the search to stagnate due to the spatial dimensionality. Conversely, removing the causal guidance deprives the engine of its early acceleration. And we can find that the true optimization accelerance is unlocked when both operate in the tandem. And to answer the third question, we test the zero-shot transferring capability of our rules onto the completely unseen and out-of-domain benchmarks. The causal tuner shows the remarkable robustness when deployed directly onto the dense and complex spec workloads. And we further introduced the Llama bench, the native benchmark extracted directly from the Llama C++ framework for real-world validation. And we found that the causal tuner treasures an instantaneous 23.21% improvement in the token generation throughput. So this confirms that the causal rules could successfully grasp the universal compiler architecture principles. And we also further perform a cross-hardware validation to test the architectural robustness. And to eliminate the hardware-specific bias or other environmental artifacts, we directly deployed the causal rules meant from our original AMD platforms to another secondary Intel platforms with the fundamentally distinct microarchitecture. And the cross-platform results indicate that the causal tuner consistently outperforms the best baselines. This result demonstrates that it could capture the universal compiler architecture interactions rather than a platform-specific noise. Finally, we also evaluate the structural interpretability of our guidance mechanism. This differs the causal tuner from other black box alternatives. A case study tracks the divergent program feature distributions, and the result demonstrates this transparency. For example, for some arithmetic-heavy code, the engine could automatically prioritizing the algebraic reductions, whereas the the control flow interface, once the PHI node density across the 0.0037 threshold, it instantly injects the passes like memory to register to optimize the register promotion. Therefore, we can find that the causal tuner establishes an auditable and red box optimization logic. Okay, let me conclude. The causal tuner transformed the compiler auto-tuning problem from a completely blind and a heuristic-driven process into a transparent white box and causal guided one. While we currently rely on some offline data for training, the future work could focus on online causal graph updates and also expanding to even more diverse benchmarks. So this is end of my presentation, and thank you for your time. Since I'm not know about the details of this work, I will try my best to take your question. And if you will find more detailed some questions, you can directly email the first author Jiaqing, and I list his email, her email in the in this. Okay, and thank you.
Questions from the audience?
Hi, thanks for the talk. So you mentioned that you try to identify features in the input program for clustering the program. And,
yes.
So do you do that offline ahead of time, or is it a part of the compilation?
Yes, this process is done offline. This is done during the stage 1, and we use several programs from the Cbench and extract their features to get some candidate subsequences.
Sorry, one more follow-up question is, you also mentioned that do you use historical data from compilations for selecting the pass sequences?
Yes, we use the historic information is from the also from the stage 1. We profile some compile sequences from programs in the Cbench, and we use this information to generate some rules with stage 2, and use these features to plus the input program, and use this information in the stage 3 to generate the final compiling option sequences.
Thank you.
Thank you.
Due to time constraint, we have to move on to the next talk. Let's thank the speaker again. Soma Par from University of Kansas. The title is Empirical Observation about Profile-Guided Optimization.
Good afternoon, everyone. I am Soma. Today, I will present our research empirical observation about profile-guided optimization for mainstream C, C++ compilers. And this is the joint work with Dr. Kulkarni from University of Kansas. Here is the main agenda that I will discuss today, and I will mention the following points. So, my main focus, research focus is the profile guided optimization. So, the obvious questions comes, what is profile guided optimizations? The compiler use specialized algorithms called optimizations to generate high quality and high performance code. So, for that we have two options, that the compiler can use static heuristics to guide the optimizations decision, and another way of approach to learn and use knowledge about the program's runtime behavior to guide optimization decision to produce code that is customized for a specific set of inputs, and that results actually a better performance and better quality code. And this process of using the runtime information to guide the compiler optimizations is called the profile guided optimizations. And now, why we will use the profile guided optimization? So, if the profile is representative of the execution input, then the PGO is expected to improve performance over the static heuristics, but if it is not the representative, then it may experience performance loss. Okay. And now, I will borrow what is the same or the ideal profile. So, the profile used for the PGO is collected with the same input that is later used during the evaluation run, that we call the same profile. And the cumulative profile is basically representative profile is averaging program's runtime behavior across all inputs, and this aggregated profile is called the cumulative profile. And now, our research actually asked several questions. So, many properties about the PGOs in the contemporary C, C++ compilers have not been studied yet or recorded. So, our main goal was to understand more clearly the behavior of the PGOs in traditional C, C++ compilers for embedded system benchmark. So, we can say more specifically how much can PGO improve or degrade performance across inputs, whether the ideal or the same profile basically give us the best binary or not, whether the cumulative profile solve the representativeness issues or not, whether there is any correlation between the GCC or the LLVM compilers, and how sensitive is generated code to change in profile data for individual optimizations, and what interesting properties that we can deduce from the profile induced code variance for any program. So, now I will come to the experimental setup. So, we use 27 programs from MyBench benchmarks, and each of the benchmark has access to 20 inputs, which we can use to generate 20 distinct profiles and 20 different binaries customized to each of these inputs. And further, we generate another cumulative binary, that aggregation of all inputs, rather we can say that the averaging of the runtime behavior of all inputs. And the whole thing and the whole experiment actually we ran for the 12 times for each benchmark, and then we averaging out and we took the standard deviations. And we use the hardware platform, that is x86-64, and we collected our results, so we present our results through 9 empirical observations. So, here the main focus is the performance analysis with the PGO across compilers. Okay. And another one, sensitivity of the individual optimizations and the profile induced function variance. Now, I will come to the point, what methodology that we use. So, here we use the instrumentation based offline PGO workflow. So, for that GCC and Clang, both of the compiler actually provide set of flags for the PGO. So, we use the instrumentation, first we instrument our source code. Basically, it's insert some additional code that help to collect the profiles. Okay. And then the instrumented binary we execute with our different inputs and we collect the profiles. And finally, after collecting the each profiles, we have a 20 different inputs, and we generate the 20 profiles. And after that, using all the profile information, we actually generate the single static binary customized to the representative profile. And now, I will discuss how actually we interpret our results. So, here in the screen we see that this is a big table. It looks like a bit complicated, but I will highlight some points that will easier to understand. And here if you see that the first thing that to interpret the results, actually we use 20 by 20 performance matrix. We generate this kind of table for each benchmark. Okay. And each of the columns represent our corresponding input, and each of the rows correspond to each binary variance. And after that, the 21st row basically it's represent the cumulative profile, and the 22nd row is the O3 level optimization. So, here in this experiment, our baseline is O3 level optimization. So, that's why is 20. If you see the 22nd row, so all cell actually gave the value is 1. So, we took the performance O3 over O3, and each of the cell actually normalize performance over O3 level. Okay. And so, few terms that I will discuss right now. So, I will mention here, and I will use these terms throughout my presentation and to analyze the results. The first thing is the PGO best. PGO best is the best result over profile guided binaries and the input pair. So, here we saw we marked with the yellow color as the 0.76 is the best result. That's the, we can say that the minimum ratio that we got, okay, for the input binary and input pair. Similarly, the maximum ratio performance ratio that we got, that is the PGO worst case. And all the diagonals that is marked with the green color is basically the PGO same. The PGO same is when we actually collect profile and the evaluation run with the same input. And I have already discussed about the PGO cumulative. The 21st row basically it's represent the performance with the cumulative binary. And now I will come to our observation and results. So, we saw that the PGO profile guided optimization. So, there are several programs in our some benchmark actually outperform O3 level optimizations. And for example, we saw 32% improvement for bit count with GCC over O3 performance, and 30% improvement for JPEG-C with GCC, and 16% improvement with PGP-D with the Clang compiler. And these all the results actually over O3 performance. And overall, an average that we saw that the GCC actually gave the 8% improvement for benchmarks, and the 4% improvement shows for the with Clang. And here I want to mention that in our experiment, the PGO best was as good, at least as good as O3 level optimizations. We never get any degradation than O3 level optimizations. And the second observation is the non-representative profile also can hurt the performance. So, for example, here we saw that the 12% degradation or the performance loss for JPEG D and 11% performance loss with the TIFF median with the GCC compiler, and similarly, so 14% for TIFF to BW and 11% for bit count with the Clang compiler over O3 performance. And these two results, basically the observation 1 and the observation 2, are quite expected from previous research. We confirm those results again through our experiment. And the most non-intuitive result that we got, that the ideal or the same profile is not always best. So, for the same and ideal, we expect that we will get the best performance, because the profiling and the evaluation run with the same input. But in practice, we saw that the PGO same is best only in about the half of the cases. In cases when PGO same does not result in the best performance, it is 2.7% worse than the PGO best with the Clang and 3.1% worse with GCC on average. So, from the main takeaway from this slides, that we can see that even the ideal application of the PGOs with perfect profile may result the performance loss or the performance degradation. And now we move to the another observation, that is the cumulative profile are a kind of a trade-off. So, this cumulative one is basically a common solution to representativeness problems, is to combine the multiple profiles into the cumulative profile. But here our results, we saw that the PGO cumul can mitigate some of the worst cases, but it cannot remove all the losses. Still we get 11% with the GCC and 12% with the Clang for PGP-D, but this is quite certain that it underperforms the PGP best because the aggregation smooths away the input specific benefit. Okay. And all the 4 observations actually lead us to another observation, that is the PGO correlates very poorly with the GCC and the LLVM, because we did not find any correlation or the similar kind of pattern in terms of performance with the GCC or and LLVM. Okay. So, then the next question is the experiment is about code variance. So, PGO can generate different binary versions of the same functions, and depending on the profile data, we want to understand how many distinct functions can be generated in presence of different profile informations. So, we already discussed that we have that 21 binaries, that the 20 inputs, another one is the cumulative profile. And now we use the Ghidra disassembler, that is tool by NSA, and to avoid our false differences, we actually normalize the registers and the addresses, and then we took the each basic blocks and all the instruction, we compared those instructions and segregate to the equivalent classes to identify the distinct function variants. And we executed almost 5,854 functions. Among that few functions, we actually got the single block functions. There is no variant, so we did not consider those functions in our results. And that particular experiment actually led us to another observation, that the most functions have a very few variants. So, since we have a 21 distinct profile, each executed functions could have at most 21 distinct code variants and one corresponding to each profile. But in practical, we saw that the several profiles actually produced identical code. For example, 87.9% functions have two or less fewer variants with the LLVM, and the 86% functions have 3 or less variants with the GCC. So, these particular experiment or the results basically suggest that the most of the functions are insensitive to the profile differences, but still there are several functions actually generate 21 different code variants. This is a kind of a Pareto-like behavior. So, we say that the most functions are still stable, but a very small number of functions account for much of the profile induced code diversity. And then we move on to another observation, that the GCC and Clang show the different optimizations behavior. For that, we use the control flow variance. We study the control flow variance for each programs. And here we plot the graph in x axis, that the number of function variance and the y axis is number of the control flow variance. So, the result that we observe here, the GCC points cluster among along the diagonals, that means there are more number of control flow variance for each function variance compared to LLVM. But whereas if you see that the Clang results or the LLVM results actually clustered in the bottom left all the functions. So, it's basically suggests the less number of control flow variance. So, from these slides or from this experiment, actually the main takeaway is the control flow optimizations are more active in GCC compared to the Clang or LLVM. And the last but not least, the observation, that is the one observation, that a very small set of variants often achieve best performance over all inputs. So, in these experiments we want to see that the how many binaries can give us the best performance across all inputs. Okay. So, for that we saw the result 5 or fewer binary is sufficient to give us the best result across all the inputs. But still there are few benchmark programs that actually give us the only a one binary that that give us the best performance across all the inputs. Say example is PGP and the SHA both actually shows the both actually provided only the single binary that that satisfy that our criteria, that the best performance across all the inputs. And these are the summary of our observations. So, in our research we study basically the 9 observations, but I will say here that there are few more observations and the interesting experiments in our paper that I could not cover in my talk. And an overall conclusion that I want to mention here, that we confirm that the PGO is a mature and valuable technology, and however, its behavior is still surprising. Profile can help performance, sometimes it is hard, some result is really expected results that we got, and some are surprising and some are very non-intuitive as well. The behavior, and the second observation is here, or the conclusion, that the behavior of individual optimizations with the profile data does not follow any common pattern across compilers. These particular observation, we can say that it actually open exciting avenues for the future research. And we believe that these issue, if we can resolve these issue, then it will enable more consistent explainable PGO across programs and the compilers. That's all my presentation. Thank you for your attention. I would be happy to take any questions.
Questions from the audience?
Okay, very nice talk. This is Rachel from Peking University, and I want to know regarding your observation tool. What can we determine whether an input is representative, or how can we get such input? Because this is such a significant influence factor for the PGO method. And what's your suggestion regarding the methodology or the principle to help us to do this? Thank you.
So you want to know what kind of inputs I use?
Yes, given input data, can we check whether this data is representative, and how can we generate such input data?
Oh, okay. So we use the MyBench benchmark programs actually that extend 20 different set of inputs. and from the real world. So we use that the 20 different inputs for analyzing the whole result. So when we run our benchmark program, so MI benchmark is almost a C bench program. It's actually, so all the C bench programs we got 20 different inputs that extends, and we ran all the C benchmark programs with the different 20 inputs, and then we saw that our baseline is the O3, right? So whether the performance we got, whatever the performance, whether it is less than 1 or it is more than 1 for our experiment. If it is a less than 1, we saw that it's basically its degradation over O3 performance, and if it's more than 1, sorry, if it is a more than 1, so we say that there is a performance loss, but if it is less than 1, then we can say that it's actually we got the improvement over the O3 performance. That's
You mean if we have several input data, we need to iterative among them to find the best one, right?
The several inputs, yes.
Yes, you have
so several inputs. If you say yes, I can show you the our. Say this is the table. So in this table, if you see that there is all the columns that were actually the 20 inputs.
Yes, you have 20
inputs. Even among all the results, so we identify which one is the best. Is the 0.78 is the best, is the binary, that the 13th binary with the 7th input we got the best results.
Yes, you have to run the program with each input data.
Input, exactly. So it's like binary, we say the binary 1, okay. So we run the binary 1 with the input 1, input 2, input 3 till the 20 input, and say similar way the binary 2 we run with the 20 inputs. So then we identify from whole table that which binary and the input pair that we got the best performance. It's like the minimum ratio over O3 performance. That's
yeah, okay, thank you.
Thank you, great presentation. So one quick question is for the non-intuitive observation that you got, I think observation 3, so same binary and profile and execution inputs are matching. Do we have an understanding of why we got lower performance with PGO? Is that a problem in the profile?
For that, okay, I want to show you some additional slides that I couldn't discuss here, but I can show you. So this is another kind of experiment that we did. So we saw that the most non-intuitive results that we got is like we saw that and after that for that result we actually analyze each of the optimization, how it's mainly because of the optimization, different optimizations. If you see that the results, see here these two graph, it's one is with the PGO presence of the profile data, and another, the next slide I will show you is it's a not presenting of the profile data, and the another one is with the present of the profile data. So here if you see this is the GCC one, and this is the Clang results without any profile data. Okay, so for the each optimization we got the performance for the each optimizations, but here we saw that this is a kind of unpredictable. It is not depends on a particular optimization. You can say that for I cannot say that for these particular optimization actually are responsible for the degradation or the same even the same profile. So rather we can say this is a kind of a cumulative effect of the all profiles. It's maybe the phase ordering is also a one one's reason, another one is the phase selection is the one, another one is that I mean carefully you have to choose all the optimizations carefully, that those actually have the benefit. And the next slides that I can show you, this is basically the with the presence of the optimized I mean profile code. So, here you see that with the presence of the same thing, it is like we just ran each of the optimization. The first graph was without any optimization information, without any profile information, and this one is actually with the presence of the profile information. Now, you see that it's lot of up and down. You cannot predict that how each of the input or how each of the workload will actually perform. It depends on a lot of cases. It depends on the workload. It may depends on the inputs. It may depends on the interdependency of the optimizations as well. So, this is a kind of open research still.
Okay, thank you.
Quick last question.
So you did show about those 20 variants, right? Like when that person asked, you did show a slide where you had 20 different versions.
So, the table one?
Yeah.
Okay.
Yeah. If you could go back there, I had a quick question. Yeah. Like just to make sure I understand it correctly. So you have 20 different versions of a binary generated with 20 different versions of profiles from their respective inputs, right?
Yeah.
So when you picked the best one there, so were all 20 versions of the binaries were evaluated against same single input, or they were evaluated against their the input that was passed to their profiles?
Yes, I mean it's a combination. If you see the same, I also discussed that one. See, in the row we have a 22 row, right? So,
Yeah.
if you see that this is basically the binary. So, when the binary is the first binary, that is profile with the profile 1, and when it's run with the input 1, that is a kind of a same profile. Okay, the same input same profiling and the execution run with the same input. But when we go for the second input, so this is the non-representative. It's like is the binary 1, but the input is 2. Input is different input, and
for the final evaluation?
Final evaluation with the input 2.
Okay. Like, wouldn't that cause confusion in terms of like maybe we can catch this offline?
Yeah, sure. Okay.
Yeah.
And you can get in my paper more details.
Sure,
I
sure,
couldn't
yeah,
discuss
sure.
all of
Probably,
the
I
constraints
missed that,
here,
yeah.
but the whatever I did, there are a few more experiments and the observation in details in my paper, so you can.
Sure.
see that one. Sure.
Another question is, did you check about splitting the sections into hot and cold and try that? Keep
No,
them
not
in
really.
different sections?
No,
like,
I didn't.
Okay. Sure. Yeah,
Thank
thanks.
you.
Yeah.
Yeah, let's thank the speaker again.
Hey, Chaitanya. Okay. And the paper title is WBB, Binary Code Size Reduction, and so on. Okay. You have.
Hello. Am I audible? Yes. Okay. Cool. Hi everyone. I'm Chaitanya, and I will be presenting DDub, a post-length technique that reduces binary code size through outlining basic blocks. This is a joint work between folks from UC Riverside and Google. First, why do we care about the code size reduction? So usually we have always seen, right, with new software upgrades and new addition of features, the binary code, the size of the binaries tend to increase. And at Google, from Google Play, of course, we have found that even about a 6 MB increase in a binary causes about 1% reduction in install conversion rates. Now, how much can we actually save? The figure measures the duplicate code in several benchmarks. The blue bars show how much the actual deduplication is done by the conventional methods. The orange bars show what's actually possible if we happen to deduplicate blocks that manipulate stack and also that are found across modules. The gap is large. For example, here the mixer benchmark has about 70% of the savings coming from stack and cross module opportunities. So, this opportunity is what motivated us to do this problem. So, now let us look at the existing techniques. The first one is LLVM's machine outliner. It runs as a compiler pass. It finds repeated instruction sequences in the program, puts them into a single outlined function, and replaces each copy with a call. Because it is a compiler pass, it only sees one module at a time. To deduplicate across multiple modules, it needs full LTO support. The second one is PLOS, a recent post-link outliner built on top of Bolt. Being post-link, it naturally works across modules, and it uses profiles to stay performance neutral, but its implementation targets only ARM architectures. The key thing is both outline duplicate code using call return semantics. Now, let us look at how these prior techniques fall short. There are 4 major limitations. First is when dealing with stack manipulating code, existing tools can only partly outline it, that is, they are suboptimal. If you look at the basic blocks on the right, wrapping these instructions in a call actually affects the stack, as call instructions are tend to push registers on the stack in x86 or clobber x30 register in ARM architecture, right. So, machine outliner here does not adjust the stack offset at all, which is required if you are going to add a call instruction in the presence of a stack manipulating code. However, PLOS tries to adjust them, but neither of the tool can outline through instructions that set up the frame pointer. For example, here as you can see, the instructions that are including and before move x29 SP are never outlined by PLOS or either machine outliner. So, this significantly is a missed opportunity in the prologs and epilogues of functions. Second is they have limited reach and scalability. For cross-module savings, Machine Outliner requires full LTO support, which is not scalable across warehouse scale or even a large scale program because of memory constraints. PLOS, on the other hand, is restricted to ARM architectures and fails to link large binaries. Third is, these prior tools are not built for warehouse scale or post-link infrastructures as I mentioned just before. Finally, Machine Outliner lacks profile guidance. If you outline hot or frequently executed instructions, you will end up hurting the performance because you are going to add new instructions in the hard path that disturbs the overall execution time of the application. Our solution here is basically DDub addresses all 4 of these limitations, which I am going to cover in the next slides. Here is the core idea behind DDub. For the cases where basic blocks touch the stack or overwrite the return register, we replace the standard call return with our save and jump technique. Here is how it works. Before transferring control to the outlined block, DDub saves the return addressed into a pre-allocated stack slot. Then it simply jumps to that outlined block without actually touching the stack. At the end of that outlined block, it simply retrieves the saved address from the predetermined stack space that we have already reserved and jumps back. So, let us look at the ARM example on the slide here. The original code in the middle is identical, which is marked in the yellow on the left most side of the slide, but the top and bottom in the same function differ because of different frame sizes which those functions use. So, Machine Outliner and PLOS can only outline a part of this, that is they cannot outline any instructions that are part of setting up the frame pointers like move x29 sp etc. So, this leaves the stack accessing instructions remain duplicated, and they are forced to add extra save and restore code inside the outlined block as well. DDub on the far right solves this by growing each frame by 16 bytes to reserve a slot for the return address. This lets us safely outline the entire identical region, giving us the maximum code reduction. We also ensure correctness for x86 architectures. There are 2 cases here. One is the red zones and the other one is how do we outline or deduplicate in the presence of a call instruction. So, on the left, the red zone, just to give a quick intro, red zone is a 128 byte scratch space below the stack pointer for the code to use, which is led by the ABI. If you outline a block that uses such red zones with a call instruction, as we know the call instruction pushes the return address onto the stack, and thereby it would affect all the data stored in the 128 byte stack space. Hence, all the accesses to that particular region get clobbered. So, DDub's save and jump here actually uses a 16 byte slot just before the caller's frame. So, the red zone accesses always stay correct on the right. On the right side of the figure, we have basic blocks that contain a call instruction. Machine Outliner refuses to deduplicate these. On the other hand, DDub actually realigns the stack by spilling a register, so that the stack gets aligned to 16 byte space, which is expected if you are going to have a call instruction. So, Yeah, so with that the blocks actually work perfectly, gets aligned with the ABI. So, the takeaway is save and jump captures cases prior tools leave without breaking the correctness. Now, let us understand more on how the patch code for save and jump technique actually works. To do this, we need a register to store the return address into the pre-allocated 16 byte stack slot. To save cost, we run liveness analysis to see at that particular program point what registers are actually dead, which we can use to store the return address onto the pre-allocated stack space. If we find a free register, we use it. If we don't, we actually spill the caller saved register R11 to store the return address. Now, let us take the same example of red zone which we saw before. If we naively used a standard call instruction to reach the shared block, as I mentioned before, the stack accesses will get clobbered. Instead, our patch code uses that scavenged register which we picked from liveness analysis or by spilling to store the return address into our 16 bytes slot we pre-allocated just before or outside the caller's frame, as you can see on the figure. Then we execute a simple jump instruction. Because the stack pointer never moves during the jump, the stack is always preserved and the red zone will never get affected, and all the stack accesses inside the red zone will be working perfectly. And just to touch on profitability, even if we have to spill R11, this entire patch is at most about 20 bytes. Since our average outline block in x86 is about 28 bytes across the workloads that we considered. So, this transformation easily pays off for itself. So, now let us walk through how DW actually scales to warehouse scale binaries using Propeller tool. First, a quick intro on Propeller. Propeller actually gives a basic block and function address mapping through f basic block address map flag. It tags every basic block with its unique ID, offset and size. DW uses this map to easily spot identical basic blocks across the entire program. Once the duplicates are found, DW feeds two simple directives back to the compiler. The BBM directive tells what copies to be used as a master copy, and the BBF directive tells the compiler, hey, this copy should be folded and the master copy remains at this particular point. Yeah. On the right is the resulting binary. You can see the new master block at the top, and the old duplicate blocks near bar function have been cleanly replaced by a jump and a call instruction. The Propeller's build system can compile each module independently, as it knows the global summary or view of the entire binary. So, this is a distributed build, and hence it scales to warehouse scale workloads. The remaining three limitations are by design captured by DW. Because DW runs at post link, it naturally sees all the modules at once. And using a quick FNV hash, we do a constant time lookup at what is actually matched, and then we have already ported to Propeller for warehouse scale application. And we observed that across the workloads that we have used, about 77% of them were actually 77% of the duplicate code or the blocks were actually cold, and hence by default we apply our DW on cold ones. This keeps the dynamic instruction count on hot paths unchanged. So, performance stays neutral while retaining most of the size savings. Now, let's look at the iterative deduplication. When a duplicate code is outlined, the patch code is added in the form of call or a jump instruction. This patching can also introduce newer, smaller duplicate sequences. Prior tools, Machine Outliner and PLOS actually reruns their entire deduplication pass to cover this until it converges. On the other hand, our algorithm always starts at merging largest basic blocks. So, the newer smaller opportunities are already subsumed. We get the benefit of iterative duplication with lesser overhead compared to theirs. Let us look at the results, starting with the small and medium binaries on ARM. This is one setting where all three tools run. So, we can compare them directly. We evaluate on top of the baseline that is already heavily size optimized using OZ and linker ICF and linker GC sections. On these benchmarks, DDub actually achieves about 2.6% average additional code size savings over the baseline compared to 1.5% of PLOS and 0.2% of MO, and with DDub leading on every benchmark. Now, let us look at the size savings, which is even more on large and warehouse scale workloads. Here we observed about 25.8% reductions on warehouse scale workloads and about 18.6% on large scale workloads like Clang, MySQL and Zalang. Importantly, we stayed performance neutral because we only targeted cold blocks. In fact, benchmarks like MySQL and Zalang, we observed about only 1% faster execution time. The build time overhead was small, and we retained over 82% of maximum possible savings. Yeah, just to summarize, there is still a lot of duplicate code in optimized binaries, and much of it is from stack manipulating and cross module blocks, which was missed from prior tools. DDub is a post length basic block deduplicator built around the save and jump sequence, which lets it capture those blocks. It scales to warehouse scale applications through Propeller, and its profile guidance keeps performance almost neutral. The size savings on smaller to larger is about 1.5 to 18.6%, and on warehouse scale it reaches up to 25.8%. Looking at the future work here, we want to try outlining on near duplicate basic blocks. So, all the techniques that I showed, Machine Outliner, PLOS and others, actually work on the basic blocks that exactly match, or the subsequence that exactly match. So, how about we extend this to basic blocks that have like only one register difference, but they're semantically same, but they're not exactly same. What happens if we scale it to this is one direction. Another direction is Google's MLGo has achieved significant improvement with inlining heuristic, where neural networks actually guide the heuristics decision on inlining. This is another direction where we would want to see if we can come up with a better cost model for choosing what to outline here. And the next lastly, we want to try about increasing the scope of our work to other architectures like RISC-V as well. Yeah, that's pretty much it from my side. Thanks for your time.
Hi, thanks for the talk. I'm curious to know how you measured the like optimal cost savings, because I think you mentioned at the end that you were approach captures most of the sort of potential cost or size savings, right?
How did I measure?
Yeah, how do you tell what's the like optimal reduction in size?
What's the optimal? Let me understand if I let me see if I understand your question.
Sorry, I think it might have been 2 slides ago.
2 slides ago. Okay. This one. Or this one?
Yeah, sorry, yeah, the last bullet point there where you say 82% of max savings kept. What do you mean by max
Oh,
savings?
yeah. So, okay. So, using the profiles, we only fold cold basic blocks. And then we measure the size of the output binary on what it was, how much it got reduced versus how much it would have gotten reduced if we hadn't applied any profiles. So, we were able to retain 82% of what it would have been if we weren't applying the profiles.
So basically, max savings means if you had outlined also hot basic blocks.
Yes.
Okay, that makes sense. Thanks.
Yeah.
Hi. Do you have any idea why larger binary sizes drives fewer app downloads?
Sorry,
Okay. Do you have any idea why, or have you looked into why these increasing app sizes correlates with fewer downloads? Like.
That has to do with, like I haven't looked at, like that's not the study I made.
Okay.
That's the
Yeah,
study from Google Play, so that's where we got. But like this is how I thought about it, right? So we have limited memory. Let's say any Android phone you can pick or any device you can pick. So if you keep on increasing, it's not good for the device, right? So after a point, somebody might say, hey, this is too big and it cannot fit in my device, or I don't want to be having this app because it is causing significant memory overhead in terms of running the application, etc. Right? Even though, let's say you download it from Google Play or anything. So when you click on an app, it has to load everything into the memory and it has to run, right? So, I mean, like the larger the size, it actually reduces or increases your overhead on running these apps.
Right.
So that's that would be the good intuition to make, I guess.
Okay, let's thank the speaker.
Thank you.
Yuanpeng Wang, who is presenting SimFlow, event chain aware symbolic execution for serverless sensitive data flow detection. Okay. Okay, wonderful. You can start.
Hello. It's working. Good afternoon, everyone. I'm Yuanpeng Wang from Peking University, and it's honored to introduce our work titled SimFlow, Event Aware Symbolic Execution for Serverless Sensitive Data Flow Detection. And it's a joint work of Peking University and the National University of Singapore. And serverless applications are naturally event-driven. A handler function may be triggered by an HTTP request and read data to a managed service. And later, another function may be triggered by that service by a queue or by a timer. And this makes the application look less like one monolithic program and more like a workflow assembled from functions and cloud services. And that workflow is convenient for developers, but it is also difficult for security tools to analyze precisely. Notice that the arrows in this picture are not normal function calls. They are event transitions mediated by the platform, so a security tool must recover context that is distributed across configuration files, handler code, and service state. And before discussing the technique, we need a precise definition. In this call, a sensitive data flow is an end-to-end value-carrying propagation from a security-sensitive source to a security-critical sink along a feasible serverless event train. And feasible is important. The train must satisfy handler logic, event constraints, resource state, and cloud service semantics. And existing research has shown that identifying sensitive data flows within serverless applications is crucial for serverless security. However, existing approaches each miss a piece of the problem. Traditional dynamic analysis has relatively low coverage, and standard small execution like serverless context and Cloudflow, a SOTA static serverless sensitive data flow analyzer, is topology only and path insensitive. It cannot validate runtime mediated flows through service state, and we found that lack of connection between topology structure and runtime validation leads to over-approximate or runtime-mediated flow missing. And here is a small motivating example. The first handler receives HTTP input and stores it into Dynamo database. The second handler is timer triggered, scans the database and passes the value to os.system. And there is no direct trigger edge from the first handler to the second handler. The dependency is mediated by a database item, and it is also item specific. A topology-based analysis may see that both handlers access the same table, but it cannot prove that the value written by the first handler is later consumed by the second. This example is potentially small, but it captures the same pattern we observe in real applications. Data is stored by one function and consumed later by another function whose trigger is not explicitly linked to the first one. And this slide shows the keep gap we addressed. Architectural reachability tells us what may be connected according to INC files, trigger declarations, and resource bindings. And semantic feasibility tells us whether the connection can actually execute under the constraints. Existing static tools often conflate these two levels. They may report paths that are structurally possible but semantically infeasible. And they may miss flows that are only exposed through runtime-mediated resource interactions. And in our work, we use this separation as the organizing principle. We first ask what trains are architecturally possible, and then we ask which of those trains are semantically executable. To analyze both architectural reachability and semantic feasibility together, we formulate three challenges. First, we must recover cross-function dependencies that are not explicitly declared as trigger edges, especially dependencies mediated by shared resources. And second, we must generate feasible event trains and inputs, because naive enumeration produce mostly invalid executions. And third, we must validate data flows paths sensitively while modeling the cloud services that connect functions. These challenges correspond directly to the three main components of SimFlow. SimFlow has three stages. It constructs an event dependency graph, explores context-aware event trains, and then performs event-sensitive symbolic execution. The output is verified sensitive data flows that are feasible under real execution constraints. And this slide shows complete workflow of SimFlow. The left part is the EDG constructor. It takes IC files and application code as input and builds an event dependency graph that connects handlers, resources, sources, sinks, and dependency attributes. The middle part is the context-aware event chain explorer. It extracts paths, constraints, and resource features from the EDG, and then generates event sequences and corresponding inputs that are consistent with the serverless architecture. The right part is event-sensitive symbolic execution. It uses symbolic inputs and cloud API emulation to check whether the data can actually propagate from a sensitive source to a security-critical sink. The key idea is that the EDG narrows the search space while symbolic execution validates feasibility. So the final report is a verified sensitive data flow rather than only a reachable architectural path. And then we introduce the three components. First, component 1 solves challenge 1 by building the event dependency graph, abbreviated as EDG. The input is IC plus handler source code. First, SimFlow parses declared triggers such as HTTP, timer, S3, Dynamo database, and queues. Second, it scans host API calls to discover which handlers read or write shared cloud resources. And third, it annotates handlers with source sink and event attributes. Finally, it adds two kinds of labeled edges. The example on the right shows the important idea. If H1 writes Dynamo database and H2 later reads it, the resource node makes that hidden dependency explicit. And component 2 solves challenge 2 by turning EDG paths into executable event trains. It starts from a source to sink backbone path in the EDG, and then adds the dependency closure. Any resource-mediated links required for the flow. Next, it enumerates valid topological orders. So if H1 must write a table before H2 reads it, H1 always appears before H2. After that, SimFlow generates or refines event inputs using EDG features, such as path constraints and resource names. The result is not an arbitrary list of handlers, but an event train witness with inputs that satisfies schemas, filters, and resource state requirements. Generated trains are still checked later by symbolic execution, so this stage gets exploration without blindly trusting the generator. And component 3 solves challenge 3 by validating the candidate train with symbolic execution. SimFlow maintains an execution context containing the current event, constraints, resource state RS, and the path condition PC. As handlers execute, the cloud host API emulator updates RS for reads and returns symbolic symbols for later reads. It also checks service-side filters, so infeasible events are blocked. In parallel, taint checking follows the source value through symbolic expressions and model cloud operations. A flow is reported only when tainted data reaches a critical sink, together with the event train witness and path constraints needed to reproduce it. Conceptually, SimFlow separates architectural paths from semantic paths. A static tool may report that a path exists because components are connected in the architecture. SimFlow asks a stronger question. Can we construct an event and a resource state that make this path execute and carry the value to the sink? This distinction is the reason SimFlow can both reduce false positives and recover flows missed by topology-only analysis. For evaluation, SimFlow is compared against Cloudflow and evaluated on CloudBench plus 104 real-world Awesome Pi applications. And this table reports the main effectiveness and precision results. The highlighted overall row shows the aggregated result, 332 verified flows, compared with 243 for Cloudflow. The gain column highlights the key result. SimFlow finds 89 more verified flow overall, and we are also improving precision by 14.4 percentage points. The precision gains comes from three design choices. First, runtime dependency modeling proves invalid cross-function paths early. Second, valid input generation steers analysis toward executions that satisfy event requirements. And third, cloud API simulation checks whether data actually moves through managed service as assumed. Together, these mechanisms reduce false positives caused by topology-only reasoning and improve the quality of reported flows. And this table explains where the additional detection comes from. For declared dependency, the gap is moderate because both tools can read trigger mappings from ANSI files, and the important gap is shown in the SimFlow runtime determined dependency column. Overall, SimFlow covers 2,142 runtime determined chains, compared with 1,060 for Cloudflow. These are the chains mediated by resources, event contents, and runtime state. So this coverage advantage directly supports the effectiveness results. SimFlow also improved vulnerability discovery. On CloudBench, it finds all 32 vulnerabilities, and on Awesome Pi, it finds 14 vulnerabilities, including all 12 found by Cloudflow plus 2 previously unknown vulnerabilities that Cloudflow missed. And this result matters because a sensitive data flow is useful only if it helps reveal a practical security risk. SimFlow's additional flows shows that the improved analysis is not only a metric improvement, but it can expose security issues that were previously hidden. And then let me walk through a concrete case. Here, an attacker controls the user remark fields through HTTP input, which handler pay order stores into Dynamo database, and handler retry pay checks, then reads it, constructs an S3 key from it, and stores back to the Dynamo database. And finally, set order reads the key and fetches the object and passes user remark into a shell command. And there is no direct trigger edge. The handlers are connected through the Dynamo database and S3 state. The key itself is attacker controlled, and the sensitive value propagates across 3 handlers and 2 services before reaching the sink. Existing tools miss the flow because while SimFlow recovers the flow train through the EDG, constructs feasible event inputs, and proves through symbolic execution that user remark can indeed reach command execution. And there are also several directions for future work. And we can broaden the cloud service model supported, and we can reduce runtime overtime by caching or incremental analysis and local model support. And third, we want to extend event train reasoning to multi-cloud and hybrid serverless deployment. Finally, we want better developer-facing explanations and repair suggestions. So confirmed flows will make SymFlow more practical for production security workflows. And finally, to conclude, SymFlow combines architectural reachability with semantic feasibility. It builds an EDG graph, explores context-aware event trains, and validates flows with event-sensitive symbolic execution. Across the benchmark, this design detects more real serverless-sensitive data flows, improves precision, and expands the coverage and discover additional vulnerabilities. The main idea is that the serverless security analysis should validate feasible event-trained data flows, not only report reachable topology. And thank you. That's all my presentation, and welcome to the questions.
Okay, let me start. So I was wondering, can you do this work with just symbolic execution, and not doing the first part, the architectural part?
Without static analysis and event train generation, symbolic still works, but it will work not that good, because first it will suffer more exploration on the invalid sequences, and I think it's not, and it will make the state explosion worse. And so I think the main contribution is to combine the static analysis and event chain generation with the symbolic execution. So I think.
Okay, thank you. Other questions? Oh, let me ask another one.
Okay.
So if, is it possible, since you brought up the state explosion problem, with symbolic execution, is there a possibility of getting less precise results but faster?
I'm so sorry.
Can you do something with symbolic execution or your approach that can reduce precision a bit but make your algorithm faster?
Yeah. The overhead of symbolic execution is large, and it is a fixed problem of symbolic execution. And I think there are many ways to mitigate this problem. We can reduce improve the solver of the symbolic execution, or we can combine the symbolic execution with more tools such as fuzzing. And I think it's a way to make more work out of symbolic execution, and it will make the work faster. Okay.
Okay, thank you. Any final questions? Okay, then let's thank the speaker again. Okay, so our next talk is an online talk, which is pre-recorded. So Caroline will play it, I suppose. So the talk is on the third one, CVS, a metric for security-aware compilation against side channel attacks in edge SOCs, and it's our first work-in-progress paper. here. Is the next presenter ready to present? Are you ready to? You're the last. Are you the next one or the one after that? Next one. Okay. Yeah. Please come. Interkernel control flow on memory mapped near data processing architecture. And Seong Hyun is going to present it. He's from Posttech.
Hello, I'm Seung-Hun Lee from Posttech, and today I present our paper, A Programming Model for Efficient Interkernel Control Flow on Memory Mapped. Oh. Sorry. Hello, I'm Seung-Hun Lee from Posttech, and today I present our paper, A Programming Model for Efficient Interkernel Control Flow on Memory Mapped Near Data Processing Architecture. To address the memory bandwidth and capacity woes, CXL memory has been recently proposed. However, accessing CXL memory can incur long latency and low bandwidth, causing data movement bottleneck. To address this, near data processing in CXL memory has been proposed to utilize higher internal bandwidth. In particular, memory mapped near data processing architecture enables general purpose NDP by extending the RISC-V architecture. In the NDP kernel, like the vector-head kernel in this example, many microthreads are created and mapped to data chunks in a given memory region called microthread per region. They execute vectorized kernels with fine-grained multithreading for high parallelism. However, the M20P architecture lacks a high-level programming model. Furthermore, complex workloads with iterative and conditional kernel launches can still suffer from long host device communication latency. For instance, in CUDA, kernel launch decisions are made by the host, causing frequent host device round trips with microsecond scale latency, including software overhead. Therefore, such a host-driven control flow degrades performance in dynamic workloads. To address this, graph-based approaches like CUDA graph launch multiple kernels as a graph task graph. By making kernel launch decisions on the device, it effectively reduces host-device communication. However, it it requires manual graph constructions as shown in this example, substantially degrading programmability. For effective NDP programming, we require a performant and easily programmable interkernel control flow support. In addition, we need a unified abstraction for architectural features like sketchpad memory and microthread provision, as well as an effective way to write vectorized kernel codes. To this end, we propose device main for intuitive device-driven interkernel control flow. Also, we provide a unified task abstraction based on C++ class. Moreover, we extend Google's Highway SIMD library for writing vectorized NDP kernels. The resulting programming model is called Arachne, and I will explain these in detail later. The device main function enables intuitive and efficient interkernel control flow. It is analogous to the main function of C++, but is entirely executed on a lightweight core in the NDP controller. This plot compares performance and programmability of different approaches. Compared with host-driven control flow, we reduce host-device communication for better performance. Also, compared with graph-based control flow, we improve programmability with intuitive interkernel control flow expression. Furthermore, we provide a unified abstraction of NDP tasks based on the C++ class. The base class NDP task bundles elements that are shared across all tasks. In detail, it exposes host callable runtime APIs and holds common task components like device main and microthread provision. To declare a specific NDP task, users simply inherit from this base class and define the task-specific components like NDP kernels, sketchpad memory, and the definition of device main. This provides a unified abstraction for the features of the M20P architecture. Finally, we extend Google's Highway SIMD library for expressive vector programming. We added some methods for identifying microthread, accessing metadata chunks, and vector atomic memory operations. An NDP kernel is written in SPMD manner, single code applied for all microthreads of a kernel. As an example, this vector-add kernel loads two vectors, adds them, and stores the results to the metadata chunk. For the evaluation, we evaluate an earlier implementation of Arachne on the M20P simulator, comparing it against the baseline host-driven control flow. For this, we chose single-source shortest path, as it has iterative and data-dependent kernel launches. Arachne achieved up to 8.3 times speedup over the baseline. The performance gain increases as the host device communication latency increases, since Arachne reduces such communication. On the other hand, the performance gain decreases as the graph size increases, since the kernel runtime becomes more dominant. In summary, existing programming models trade off programmability and performance in interkernel control flow. Our model, Arachne, enables effective NDP offloading through device-driven control flow with device main, class abstraction of NDP tasks, and highway extended for M20P architecture. As a result, Arachne achieved up to 8.3 times speedup for SSP over host-driven control flow, while enabling intuitive kernel programming for M20P. As ongoing work, we plan to evaluate Arachne with additional workloads and support asynchronous kernel launches in device main. Thank you for listening.
questions? Okay, let me begin. I'm not aware of the M2 NDP architecture. Is this something different, or is this approach also applicable to GPUs, for example? So is your approach specific to M2 NDP, or can it also be applied to just GPUs?
For now, it is only applied for our the architecture M10DP, but the approach is like device mains. I think it can be also applied, but for GPUs, but the implementation is not ready.
Okay, it's not available. Okay, and do you see when you move the control flow from the host to the device, do you lose anything? For example, debugging ability or anything of that sort.
Debugging ability.
Because you're moving a group of kernels now.
Yes.
So it would be harder to stop after each kernel, for example.
That should be handled for the future work, I think. So.
Okay. Thank you so much. We think about it. Okay, let's thank the speaker again. So we are going to try the previous talk again. Next one. Okay, they tried it again. Okay, so we'll go to the final work in progress talk of this session.
Good afternoon, everyone. My name is Yihan from the National University of Defense Technology.